Chapter 14 is going to cover basic probability and probability rules. The first rule of probability is that it has to be a number between 0 and 1. So that formula just looks like probability of A has to be greater than or equal to 0, but less than or equal to 1. The second rule is that a legitimate probability model must sum to 1 or 100%. And then the formula for probability is going to be favorable outcomes divided by possible outcomes. The third rule is the complement rule. The complement of event A is that event A does not occur. So to find the complement of event A, you would just do 1 minus the probability of A occurring. So an example of this is if event A is the probability that you get red. The probability that you get red is 0.8. So what is the probability that you don't get red? Or what's the probability of the complement of red? And you would just do 1 minus 0.8 and you get 0.2. The law of large numbers states that the long-run relative frequency of repeated independent events settles down to the true probability as the number of trials increases. This is often confused or mixed up with the law of averages. The law of averages is the misunderstanding that probabilities are supposed to compensate somehow to whatever happened in the past or even out. So the major difference here is, let's use the example of flipping a coin. If you're flipping a coin, you know the probability of you getting a heads is 50% and the probability of you getting a tails is 50%. In the law of large numbers, let's say that you've flipped the coin 3 times and you've gotten a heads. Well, if you were to keep flipping that coin 100 times, 1,000 times, the probability, the true probability is going to end up being about 50%. About half of those should be heads, half of those should be tails. It eventually evens out. Whereas the law of averages, using the same example, would be if you thought, okay, well, I've gotten a head 5 times. So you think that you have a higher probability of getting a tails the next time, when really the probability of you getting a tails that 6th time is still 50%. The probability doesn't change just because you've gotten a heads every, the other 5 times. 2 events are independent if knowing one event occurs does not alter the probability that the other occurs. An example of this is if you were rolling a die and you rolled a 5. Knowing that you rolled a 5, if you're going to roll again, that doesn't alter your chance of rolling a 6. So the probability of rolling a 1 or a 5 does not change the probability of rolling another number. The probability is always going to be 1 out of 6. Now, drawing cards with replacement is another example, and note the with replacement. If you were to find the probability of drawing a heart, and then you put that back in the deck, the heart that you drew the first time isn't going to affect the probability of whatever you draw the next time because you replaced the card. So one does not affect the probability of the other. Disjoint events, also known as mutually exclusive events, are 2 events that do not share any outcome. The equation or the formula that goes with this is the probability of A and B is equal to 0 because A and B cannot occur at the same time. So if you look at the Venn diagrams below, the first Venn diagram represents mutually exclusive events. So the first event A would be aces and event B would be kings. Well, drawing aces and kings are mutually exclusive. If you were to draw one card and I said, what's the probability you're going to draw an ace and a king? Well, you can't draw an ace and a king at the same time. They cannot occur at the same time, so they are considered mutually exclusive. Now, if you look at the second Venn diagram, you see hearts and kings. And so if I was to say what's the probability of drawing a king that is a heart, you can get a king that is a heart. So those are not mutually exclusive because there is a chance that you could draw a king that is a heart. Whereas again, mutually exclusive cannot be both. They cannot occur at the same time. There are two ways to apply the multiplication rule that we're going to talk about. It just depends on whether or not we have dependent events or independent events. Remember, we talked about independent events, and something is independent if knowing that one thing occurred does not affect the probability of the other. So we are going to look at the same example with just one little thing changed. So in this example, we have a bag that contains 10 red and 10 black marbles. We're going to remove a marble from the bag, record its color, and in the first example, we are not going to replace the marble. We are not going to put it back in the bag. Not putting it back in the bag makes this a dependent event because that's actually going to change the number of marbles that are in the bag. And then for the second example, the independent event, you are going to replace that marble back in the bag. So just take note, that's the main difference here. I'm going to work out the dependent problem first, or the dependent example. The formula for the multiplication rule, if you have a dependent event, is the probability of event A, and B is going to be the probability of event A times the probability of event B, knowing that A has already occurred. All right, so our events A and B, event A is going to be drawing a black marble the first time, and then event B is going to be drawing a black marble the second time. And again, the question says, what is the probability of getting 2 black marbles? So the probability of getting 1 black marble the first time is going to be, there are 10 black marbles, so 10 out of, there are 20 marbles total. So that's the probability of event A, all right? And then we need to multiply it times the probability of B given A has already occurred. So remember, we are drawing that black marble, we are not putting it back in the bag. So how many marbles are left in the bag? Well, now there's only 19. All right, so there are only 19 marbles left in that bag. How many of those are black? Well, if we know event A has already occurred, event A was that we drew a black marble. So I know now that I only have 9 marbles left that are black. All right, so 10 out of 20 is 1/2 times, this is 9 out of 19. 1 times 9 is 9. 2 times 19 is 38. The probability of getting 2 black marbles, if you do not replace that black marble, is 9 out of 38. All right, so then we're going to do that same problem, but again, we're going to use the multiplication rule as if this was independent. So here we are going to replace that marble. So the probability of event A, remember event A is that we draw a black marble the first time. So that is going to be 10 out of 20 times the probability of event B. The probability of event B, we've got that we're going to draw a black marble, but we did replace that marble. So the probability is still 10 out of 20. So this is just 1/2 times 1/2 is going to equal 1/4. So the probability of drawing 2 black marbles is 1 out of 4. All right, the last formula we're going to talk about is the probability of finding at least one of something. The formula is the probability of at least one equals 1 minus the probability of none. The example we're going to use is, what is the probability of picking at least 1 heart if you draw 4 cards at random from a deck with replacement? So the key word that I see here is the probability of picking at least 1. And then I also see with replacement, so this tells me that this is going to be an independent, these are going to be independent events whenever I do my calculations. So the probability of at least 1 heart, I need to do 1 minus the probability of no hearts. So let's talk about the probability of actually getting a heart. The probability of getting a heart whenever you're drawing from a deck of cards is 1/4, because there are 4 suits in a deck. Now the probability of not getting a heart is the complement of that. So the probability of the complement, so we've got the complement, is 3/4. All right, now this is just the probability of not drawing a heart. We need the probability of not drawing a heart so that we can plug it into the formula. All right, so the probability of not drawing a heart, remember we are doing 4 cards, so the probability of no hearts out of 4, we're going to draw 4 times. So the probability you don't get a heart the first time is 3 out of 4. And remember, we are replacing, so that is not going to change the probability of getting another heart. So times the probability of not getting a heart, times the probability of not getting a heart, times the probability of not getting a heart. These are independent events. This first card you draw, the probability of not getting a heart is 3/4. The second card you draw, the probability of getting a heart is not getting a heart is 3/4. Third card, fourth card. Again, it's 3/4. It doesn't change because these are independent events. It tells you in the problem with replacement. All right. And when you calculate this, you get 0.3164. So 0.3164. All right, but this is not my final answer. Remember, this is the probability of getting no hearts if you draw 4 cards at random. We are going to do 1 minus that. So 1 minus all of this, 1 minus 0.3164, and you get 0.6836. This is your probability of getting at least 1 heart. So that means that you could get 1 heart, you could get 2 hearts, you could get 3 hearts, or you could get 4 hearts. This is the probability of all those combined.